We are now recording. We weren't recording before, but again, to encapsulate what might have been missed, no problem. That's my fault. I'm sorry about that. I forgot. So to encapsulate this part of it, this is sort of where the difficulty is going to peak, and then it will go down after this chapter so we get the context of our observations in astronomy. Because remember, all we can do is see stars from far away. We can't visit them. We can't get there. So our information is all very remote based on telescopes. And so now we get to the point where we will learn about light and matter. All right, we want to talk about light and matter and how they interact. And that will give us how we create instruments to learn about the greater universe around us. The text is due, that's on Blackboard. It is due April 8th. You're going to have to look at those assignments. They tell you when the due dates are. The exam will, or the first quiz will probably be due also on the 8th. I want to get that done before spring break. Actually, I might move it to that Friday so that with the idea that you get it done before, but if you need the extra time, it'll be due that first Friday into spring break. And then we'll have a quiz due pretty regularly after that as when we come back. Right now, as far as I know, spring break is normal for LaGuardia Community College. I don't know if that will change or not because things seem to change every day, but we're getting pretty close and no one said anything. So I go with what I get. Please keep in mind that the LaGuardia schedule is different than the regular CUNY schedule. Their semester, for instance, ends in the middle of May, and they started in January, whereas we start in March and go to the end of June. So we're sort of in this for a longer haul than they are. So anyhow, so what is light? What is matter? How do light and matter interact? Let's get to it. Light can be pretty difficult to hold on. I have to look at that later. So light is pretty complicated. And we'll be able to describe it in two very different ways. So before we do that, I want to establish something that will take us sort of all the way to modern physics. We're sort of skipping a lot, but I want you to think about this as we talk about light, all right? Which is the difference between how a wave, something that's a wave, would move, and how particles would move. Now particles are like hands, right? That clap was probably unnecessarily loud. They scatter off each other. Particles will reflect and bounce off each other. Whereas waves will pass through and add, they'll have superposition and then move through each other as if they never interacted at all. So to behave like a wave and to behave like a particle is two very different things. And for those of you who are a little familiar with quantum physics or who know a little bit about it, we'll probably see where I'm going with this, but we'll get there. So the first way we're going to introduce light is a electromagnetic wave, all right? And there's a little bit of it we can see. You'll notice you have white light coming in here, and you have the rainbow coming out of the prism, so you can diffract this white light. Now, in physics, colors are associated with frequencies, all right? So orange will have a very specific frequency, blue another, and if you look at the 79 Crayola colors, it's just different variations on those frequencies. Or those specific frequencies. Now, white and black, under this definition, are not colors, because white is a transmitter of all frequencies, and black is an absorber of all frequencies. So both contain all frequencies, but behave very differently. Okay? You'll notice the white light here can be broken up into all the colors, and if you have all these colors on a very absorptive surface, they'll all get absorbed, you'll see nothing back. So the energy is still there. And I say energy because we'll see that the frequency, the color of light, also indicates its frequency. Now that being said, see this part of the rainbow? This is the visible part of the electromagnetic spectrum. Basically what that means is that in all these other parts, your eyes are not designed to see and process. So one of the things we do in astronomy is we build sensors that act in different parts of the electromagnetic spectrum that give us data that we can then interpret. Okay? So for instance, when we have in the lab at LaGuardia, we have something called the scanning electron microscope. So visible light can only go down to, you know, say a bacterium or a micrometer. You can't see proteins and things like that. Well, with a scanning electron microscope, you use electrons, which you'll notice are over here, and you can create data and which can process an image. And we know that those are correct images because, one, they're too ordered to be random, and two, we can use the scanning electron microscope to compare with images of things we can see in visible light and see if we get the same thing. All right, you'll notice that if an object is smaller than a wavelength of visible light, all right, and we'll talk about that term in a minute, wavelength and frequency in a little more detail, you can't see it. All right, if you're bigger, you have multiple wavelengths that can reflect off and form an image in your eye. Those are the things you can see. Okay, so you'll notice that the higher the frequency, the lower the wavelength, and the more energetic the light, all right, or the electromagnetic spectrum. So I will use electromagnetic energy or electromagnetic wave and light interchangeably. And you'll notice that not all light is visible. So on Earth, there are sources for all sorts of electromagnetic radiation. And in the universe, there are sources for all sorts of electromagnetic radiation. All right, and we actually have telescopes that can view different parts of the infrared spectrum. And a lot of our understanding comes from seeing things, seeing parts of the spectrum with telescopes that we can't see. Okay? Now, in order to understand what a wave is, or what an electromagnetic wave is, we have to understand some of the properties of a wave. All right? So the wavelength is the distance from the peak to the peak. You'll notice that a wave repeats, right? So you could draw this wave out to infinity if you wanted, and it would go on forever and ever and ever. All right? This is an example of a mechanical wave. So that's the wavelength, and I want to see if we get to the next part, if it just comes up. No, we don't get to see that. Okay, good. So the wavelength is that length between the peaks, and the frequency is how many times cycles you have per second. So a low frequency, if you can hear, I'll click on the microphone. Hold on, I need to okay. So, ready? Can you hear that? The tapping? Okay, that's low frequency. This would be high frequency. All right? It happens many more times in 1 second than the original. All right? My poor desk. So as you can see here, the speed of light, well, oh, I almost drew the wrong thing. Let me go to the pencil. Now, recall that the speed of light is constant, right? It equals 3.0 times 10 to the 8th meters per second. And for all waves, the wavelength times the frequency equals the velocity. So if v is equal to c, the speed of light, we have the wavelength, that's a Greek lambda, by the way, in case you're wondering what it is, equals c. So given the wavelength here, right, of 1 centimeter, 0.5 centimeters, 0.25 centimeters, right, we can figure out the frequency because we know the wavelength, we know the velocity, we can find f. All right, so you'll notice that for an electromagnetic wave with a wavelength of 1 centimeter, it has a frequency of about 30 gigahertz. No, there are not going to be math questions on the quiz. You shouldn't have to calculate anything. All you should have to do is, you might have to identify something. So here's an example. I don't want you to calculate a specific frequency. I do want you to know that as the wavelength gets shorter, the frequency gets higher. That's what I might want you to know, okay? So that you understand that. And that shorter, that shorter wavelength means higher frequency, means higher energy. That stuff I want you to know, but I don't think I have any calculations on there. That's not the point we're doing, but seeing them can sometimes make sense of what we're talking about. So I want you to see it in lecture so that you get some context for what we're talking about so that it's not mysterious. But yeah, I don't really have you do a lot of math. I don't think I have you do any math in the course. At least no one's complained about it before. So it's not my intention to do that. So this is one of those ones where I wanted to show you the simulation and move things, but that's not going to be available to us. It's just going to be a drawback. I'll try and find something because I think we'll be able to, if we can start reviewing Spectrum, we should see on more than 1 week. So I'll definitely want to review basics of Spectra and show it to you a couple times. So hopefully I'll find a simulation that works for us by the end of the week, and by next week, so that we can see that. It's just there's a tremendous amount to plan and look at, and not all of it works like you plan it to online, unfortunately. So now you'll notice I just talked to you about, and this is sort of an asinine slide, right? I just talked to you about waves, and now it's just saying here without any explanation that particles of light are called photons. Each photon has a wavelength and a frequency. The energy of the photon depends on the frequency. Now this is all very important, but without context, it doesn't make a whole lot of sense. And photons were for a while a controversial idea. In fact, it was the idea of the photon that Albert Einstein won his Nobel Prize, not for the theory of relativity. But basically, the idea is that light travels in discrete particles and packets called quanta. And if you're asking yourself, how can light behave like a particle and be a wave, and if you find that confusing, welcome to quantum physics and the rest of science. So, yeah, you might just want to, as far as printing goes, you might just want to do the best you can and write things out and just use it as a reference. Because remember, I'm not collecting that ditto. So if you're worried about how do I turn in this thing I can't print out, you're not supposed to turn that in. So keep that in mind. There's no real need to print it out. You should just if you have some spare paper or something, you could just use it as a guide to answer the questions. I don't need to see it, and I won't look at it. I want to look at the written essay, which should be separate. But you want to fill in that activity sheet. You want to do the activity because that will make writing the paper super easy. So back to this. So wave-particle duality is the fundamental cornerstone of quantum physics, and it is not something that has a good explanation or that is well understood. However, keep in mind that quantum physics is the most accurate and precise theory of science in existence. So even though its foundation is a little weird, its results are very okay. Still, yeah, printing might not be an option, unfortunately, because I think they have closed campuses. They hadn't when we first started the distance learning, but you might want to check LaGuardia. They might have some stuff open, and they might be able to print and have you go to school and pick it up. I don't know. There might be services. You'd have to look into it. I'm not really sure what they are. If you look at your LaGuardia live email, that stuff will be there. And for those of you who don't check it, that option is no longer viable anymore. You need to check your school account for stuff like that and that kind of information. But anyhow, so if you look here, what I like, what you'll notice is that, and why I mentioned quantum physics is because you'll notice that the energy, photon energy, has this constant h, which is this really teeny tiny number. All right, you'd have to draw 34 zeros to start writing this 6. It's a very small number. And whenever you see an h, that indicates that you're looking at a quantum phenomenon that requires quantum physics. So we're going to talk a little more about, you'll often hear the word photon thrown around quite a bit. There was a very famous physicist who's famous in physics, but you probably wouldn't have heard of him, named Willis Lamb, who thought that photon was a dirty word and tried to stamp it out, and spent his, and after he won a Nobel Prize and, you know, did a whole bunch of really cool physics stuff in physics, he did a lot of fundamental work with the laser, and is the Lamb behind the Lamb shift, which is a fundamental aspect of quantum physics. He tried to spend the rest of his career trying to show that the photon was a bad idea. And he almost did it, but then he actually ended up proving its necessity in a few systems. So you know, so it's a confusing term. It gets a lot of a bad rap, but you'll hear it used with electromagnetic wave interchangeably. But you should always think about that, because that's always something you should think deeply about, whether you're talking about an electromagnetic wave or a photon, and when one is appropriate and when the other is not. So now that we've talked about light, and you should be sufficiently confused, we also have matter, which, big surprise and reveal, we'll define as a particle, but we'll find does have wave-like properties. Again, that's when you get to quantum mechanics. You get to the de Broglie wavelength. Now, this is pretty interesting. So you're looking at a bunch of points on the screen, all right? So if you look at this point, it says here that 10 million atoms could fit edge to edge of this dot here. All right, so if we blow this up to be 10 to the minus 10 meter, we get something that looks like this, right? This is the electron sort of popping in and out of different positions very rapidly, right? There aren't a ton of electrons. And the nucleus, this dot, is 100,000 times smaller than the atom itself and contains almost all the mass. So an atom has a nucleus, which is very dense and is at the middle, and then these electrons, and the electrons sort of flicker into different positions, in and out. They sort of sparkle like the vampires from Twilight. Okay, terrible reference, but I mean, it's kind of what it is, just at very, very small scales. I was sort of shocked and appalled when I saw that scene. In fact, I think that's the only 10 minutes of that movie I've seen. I don't want to talk about it anymore. It was traumatic. So anyhow, that's what we mean by electron cloud, and you'll notice that the sizes are pretty dramatic, right? So we live on the scales of meters. Atoms live on the scales of 10 to the minus 10 meters, and nucleuses live in the scale of 10 to the minus 15 meters. So things get very tiny when we're talking about the atomic realm, and this is the scale at which quantum mechanics dominates. All right. So in order to learn about matter, we want to, you know, the fundamental building blocks of matter, sort of we understand it, are atoms, right? I mean, there are protons, neutrons, and electrons. When we look at different substances on Earth, they can be broken down elementally. So atomic terminology, the type of atom we have, will depend on its atomic number, which is the number of protons in the nucleus. And the atomic mass number is the number of protons plus the number of neutrons. Now, in neutral atoms, that number is the same, so you just double it. However, there are these things called isotopes that have more neutrons than protons. All right, we'll talk about those in a minute. So you'll notice for hydrogen, the atomic mass number is 1. There's 1 proton, and so the atomic number and the atomic mass number are the same. Helium, even though its atomic number is 2, it has 2 protons. Its atomic mass number is 4 because it has 2 protons and 2 electrons. You'll notice a little bit of a denser electron cloud. Sadly, they use the same graphic. They could have been a little better with this. That's just laziness on their part. And carbon has 6 protons and 6 neutrons. You'll notice these are all neutral atoms. All right. Oh, right. That's not going to work. So if we look here for carbon, you'll notice that isotopes of carbon exist. So different isotopes of a given element contain the same number of protons, right? So for carbon, we can see here, they each have 6 protons, but they have different numbers of electrons. And basically, the isotopes are generally what we call radioactive, all right? So for instance, have you ever heard of radiocarbon dating? Well, you do that with this C14, and you can tell so basically, when you have a process that creates carbon, it creates a fixed ratio of C14 to C12. All right, so this happens in an active carbon process. Like your light, like as you create carbon, as the organic processes in your body create carbon, it creates a fixed ratio of C14 to C12. When you die, you stop creating C4, you stop creating carbon. The C12 is stable, the amount of C14 decreases. This leads to a decay in the amount of C14 over time, and so therefore you can tell how old something is based on the current C14 to C12 ratio. All right, so isotopes are darn useful. Some isotopes have half-lives in the microseconds. Some isotopes have half-lives in the tens of billions of years. All right, it just depends on what kind of isotope it is. Even hydrogen has isotopes. All right, you can have what they call heavy water, which is deuterium, which is a hydrogen with one neutron. You can also have something called tritium, which is important for thermonuclear weapons, which is 2 neutrons plus 1 hydrogen. Okay? So usually in class, I would give you a nice breakdown of how nuclear weapons work, but since this is being recorded, not that the information I have isn't available in tons of places, but you never know what's going to be classified or not classified, so that's something we're missing out on. Nuclear weapons are kind of fun to talk about, but they're pretty scary to realize in real life, which makes them fun to talk about because they're pretty terrifying. If you don't believe me and you want to, and you're not upset enough with the pandemic, look at some pictures of the aftermath of the atomic bombs being dropped on Hiroshima and Nagasaki. It's really upsetting. It's really terrifying. It's hundreds of thousands of people just killed and millions were infected with radiation poisoning. It's really awful. So yeah, if you want to see what those weapons do, the process of how they work, fascinating. Their use on people, atrocious. So, and like I said, if you don't believe me, there are pictures on the internet you can look at. But understanding the atom helps us not understand the atomic bomb, but it helps us understand stars and how and processes in the universe. So anyhow, now we want to get to, now that we have an idea of what matter is, we talk about how they interact. All right? So usually I have a laser pointer, and this is easier, but I want you to look at a light in your house. All right? Just find any bulb, find one around you. The light you're looking at now, from that is being emitted from the light bulb. It's a source. That's emission. Okay? Now I want you to look at your shirt. All right? You'll notice the light coming from the light in your house is probably one color, but you can see different colors on your shirt and in the room you're in. All right? If the source of light is the sun, you'll see more vibrant colors because it's a better source that can reflect more. If your lights aren't great, you'll probably notice that the colors are dimmed. That's all you can see. So absorption and reflection. We're talking about absorption and reflection. The more darker something is, the more it absorbs. So if you have a black surface anywhere, that would be absorption. If you have a single color, all that light is absorbed, and then the one color, so I have a green shirt on, right, which I think you can see. Maybe not. My light is getting pretty dim. That is being reflected, whereas the other stuff is being absorbed. Now, transmission is a little weird. If you have a light source, if you look outside and see light coming through a window, that light is being transmitted through the window. So there's a source, and then the light has to get transmitted through the window. If you walk by a wall, you'll notice it blocks the light. So it's not being transmitted, or it's being reflected back outside. So we have a little picture here, I believe. That comes next. Okay, this picture will make the this picture will make the case, but this picture we're going to look at in a minute will describe all of the different things light can do. All right, so you'll notice you have transmission through a window and things like that. But before that, we want to go back to this slide and look at the difference between reflection and scattering. Now, this is where usually we're looking at a screen, and if you look at a TV screen, think about the difference between looking at a TV screen and a mirror, okay? With a mirror, you can position a mirror so that you can see different things depending on where the mirror is. That's reflection. The light reflects and behaves specifically at an angle of incidence equals the angle of reflection, okay? And with a mirror, you can see that, right? You just go in and see different things with a mirror. Now, scattering is different. That's more like your TV. Although a screen is a better is a better example of this, because as you can see, the projection booth is shining light and the light is scattering, because like if you're at a movie theater, you can see the screen no matter what seat you're sitting in, right? It doesn't just go to one seat. Your seat doesn't change your image. And in the classroom, we'd see the same thing. It's not, you can't really say that about your TV, because most TVs are LEDs. So most of what you're seeing now, if you're looking at a monitor, the light is actually a source coming out to you, okay? They're backlit LEDs, and you have light that's being transmitted through some glass or something, and you're looking at a source transmitted through glass. So it's different. It's not quite scattering. But the light does get, goes in different directions. I'm looking at my screen from different angles, and I do see differences. Sadly, that's how I know I'm not looking at pure scattering. But but that's how you can tell there. Now we want to look here, okay? And we can see the different things going on. You'll notice we have the sun and a lamp. These are two sources. They both emit light. The mirror will reflect the light, and we can look at the different colors. The chair is red because all the light here will be absorbed, but red will be reflected back. And you'll notice that's what this guy sees. He sees red. And again, all the light will be absorbed except blue. Blue will reflect. And the same thing with the hat, right? Green will be reflected, but the other light will be absorbed. You'll notice here the sunlight scatters on snow, right? The snow absorbs sunlight, which aids in the melting, but most of it's scattered, which is why snow looks white. And the glass transmit all colors of visible light. Now, what's interesting here is that just because you transmit in one regime of the electromagnetic spectrum does not mean you transmit in another. So glass is very transparent in the visible range, but it is actually more like a mirror, okay, in the infrared range, or in the thermal, in the infrared range, which is in the thermal. In fact, if you have a thermal camera and you shine it in front of glass, you're just going to see the glass reflected back at you. Whereas the wall, which does not transmit visible light, can transmit, is more transparent to radio waves, right? Or infrared, right? The heat can go into the wall and permeate through it. And for infrared, for radio waves, like you can use Wi-Fi a bit through the walls. It degrades the signal, but it goes through. So what is transparent and what is not transparent depends on what your wavelength is. And things that look transparent to us and solid and are reflective to us, if we had eyes that saw in radio, would be completely opposite, right? So if you saw in radio waves, your windows would look like mirrors and walls, and your walls would look like windows. Kind of neat, huh? So we won't do the one thought question we do will be in this chapter. But if you're worried that we have another hour left, keep in mind we're going to wind down at around 5 or 10 after, and then you'll have that time to work on your activities. I'll stop recording, but I will be available in the Blackboard Collaborate room to just answer questions you have while you're working on it. And then I will be available on Skype on my office hour from 7 to 8. Okay? So keep that in mind. All right. Now that we've sort of learned what light and matter are, what can we learn from light? And this is where I really wish we had those simulations. I'll sort of explain to you what they are and how they work, but we won't be able to see them. So if you were to look at an object, say a dot in the sky, you might get something that looks like this. All right, and there's three basic types of spectrum. So there's emission, which you can see here. There are these dark spots and these bright fringes. All right. You can see there's a continuous spectrum. Some of it's brighter than others. You'll notice that it's pretty dim here in blue and green and pretty bright here in red. And you'll notice you get a nice rainbow looking element here. Now absorption lines, you'll notice you sort of have a dip between two continuous parts. And if you look at it here, absorption spectrum is pretty solid, but it's missing very specific colors, right? Very specific bars. So it's sort of the inverse of emission spectrum. And you can see the difference here. You see there's another little absorption spectrum over here in the far infrared. All right? And so these combinations of these spectrums give us the characteristic of an object. And you'll notice we have intensity, right? That's how bright light is versus the wavelength. Okay? So we're going to actually try and identify this object from the spectrum. Okay. But how does the spectrum give us information? Well, what we would see here, and what I'm going to try and do instead, I'm going to try and find the slide with it. We're going to sort of do this in different orders. You know what? It's too far because I want to go over that, but I want to show you. Hold on. Spectra of elements. Okay. Spectra Astro. All right, let me see here. So I'm going to share my screen with you all. Hold on, just very quickly. And I had to get this off a research paper, so it's not, it's not perfect, but we can see. Uh-oh, where did I go? Oh, here we are. Let's share an application. I'm not going to try and figure out all this. We'll just share the entire screen, and only screens with sites that you trust sharing can allow. Okay, so hopefully you can see my screen, and I'm going to make this part. Oh, gee, really? Hold on. Hopefully you can see the spectrum here. I'm going to make this the whole thing. Over on the left here, I can't really make it much bigger unless I copy the image and do a bunch of stuff to it. But let's see if I can view the image. Okay, here it is in the center. So hopefully that's what you mean. Is everyone seeing the image? Could you let me know of the spectrums? Let me see, because I can't see both. Uh-oh. All right, so we saw it, and now it's gone crazy. We've gone into the infinite loop. All right, so I'm going to stop sharing the screen. Well, let's try that again. Oh, Lordy. Holy moly. Allow. So it looks like everyone could see it. So I'm just going to talk about it as if you can. Oh, you know what? It's not working. So let's go back to the slides, because that's not going to work. I'm going to just go ahead and find one, because that's going to take less time than trying to find making the internet work. Here we go. I don't know why they took this long to get something like this. Here we go. So this is a, you can all see this now. We're back and everything's fine. All right, so this is what we saw before were absorption spectrum. These are simply emission spectrum. Now these are Doppler shifted, but so that's not exactly what we want. I don't know why it did not occur to them. Probably because they had this thing. Hold on, this is not what I want to look at this point. Oh God. How about they just, this is getting frustrating. All right, and the ice cream truck is, okay, so I will put something in for next time because this is a bit ridiculous. I could have sworn this was here. And right after this, for instance, so you know what we'll do is we're going to go over some examples in the slides of the emission spectrum and the different types of spectrum and how they work, and then we're going to stop there because I need some examples of spectra to show you what they look like, and this is not working. Again, I was a little caught off guard because of all their spectrum are on these simulations that do not work all of a sudden. So I want to yell at my computer, but I will not because that would be unprofessional. So let's go back to where we were, and we'll continue here. Got the attendees. All right. So let's look at the three types of spectrum. So continuous spectrum is like something we saw in the beginning of the chapter, where we have a prism and this white light source, and you'll notice that the prism lets everything refract through it, and you get this nice rainbow, and you have this continuous type spectrum, right? So this is an incandescent bulb. It spans all visible wavelengths without interruption. All right? So you'll notice the smoothness there. So a gas cloud of light might emit very specific colors. You'll notice the prism is still here, but the light from the gas goes through the prism, but you'll notice that only very specific colors emerge. And we're going to talk about that. This is actually a consequence of quantum physics. And what quantum physics does is predicts the way in which these spectrum lines will form by looking at the energy levels of different atoms. All right, so it directly makes this prediction, which is pretty cool. But you can see that the spectrum intensity here, you have these spikes and mostly darkness around them, right? The floor is very dark at 0 here. And now if we look at absorption spectra, which we saw an example of, if we do that, then we can see that light can be shown through a gas, and some of the light will be absorbed into the gas, whereas the rest of it will make it through. So it looks almost continuous, but these colors, right, these got stuck in the gas. And again, you'll notice these are very sharp peaks or dips, and quantum mechanics predicts those as well. All right, it's the same thing as the energy, the same process to predict those. So those are our three types of spectrum. And basically, what I want to go over, we'll at least get one spectrum, is you can quantum mechanically for any element solve this energy distribution, and you get a unique energy distribution, which means you get a unique spectrum. Now, ideally, we would have more spectra to see than, I think this is just hydrogen, and we'll see more next week, but you'll notice with hydrogen, with the gas, you have unique lines for hydrogen, okay? Of course, you can't see that because you're not seeing other spectra next to it, but we'll look at a bunch of spectrum next week, and we'll see that this is the case, all right? And basically what happens is that when an atom or a molecule absorbs a photon, you know, an electron can be promoted to a new higher energy. And that if that electron goes down, it emits a photon. And the distance, this is an energy diagram. So remember that energy is related to color. If you remember, if you recall that, no, E is equal to HF, right? So if we look here, each of these energy, these are all energies, right? That's E1, E2, and so forth and so on, right? Each of those will correspond to a frequency, and each of those frequencies will correspond to a color. Remember, F implies a color. Okay? So, spectroscopy can basically act as a chemical fingerprint and identify any element in the universe. Every element will have its own spectrum, and interestingly, even molecules, as you know, so like as hydrogen, say, bonds with an oxygen to form water, there'll be specific molecular spectra as well. So we can actually use the same thing to identify molecules as well. All right. So due to our lack of spectra, I want, so we have these nice simulations. I'm going to try and get those to work. I don't know what kind of luck I'll have, but this is a good place to stop for today. So what I want you to do over the next hour is use this hour to work on your assignment. I'm going to stop the recording though, and I'm going to just be available for questions. So, yeah. Where's my little video? There I am. So we're going to stop recording, and I will just be around. Go to Blackboard and start working on the activity. That's what we normally do in class.